Hello and welcome back to Fourier Transform, the video series where we talk a lot about the construction of Fourier series. And in today's part 8, I want to talk about an important inequality and an important equality we have for such Fourier series. However, as always, before we start with this, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a supporter, you have access to additional material like PDF versions, quizzes and other stuff. Just use the link in the description and there you can see the easiest way to get access to the material is to use the Steady platform. Okay, then I would say let's immediately start with the topic that we have learned in the last video. In particular, now we know how to calculate a whole Fourier series for a given function f. The only restriction we have is that f has to be 2 pi periodic and integrable over one period. And then we can simply calculate the whole Fourier series for it. And this means for every natural number n, we have a trigonometric polynomial we call fn of f. Moreover, we know the best way to write it down is to use exponential functions. Because then it's just a sum from minus n to n with ck e to the power ikx. And the complex numbers ck are the Fourier coefficients which are easy to remember in this form. Namely, it's just 1 over 2 pi and then we have the integral of f where we also have e to the power minus ikx inside. Obviously, this integral exists by assumption, therefore this trigonometric polynomial is always well defined for every n. However, please recall, we got all of this by discussing inner products in L2. So we get this general result here for every f in L1, but the whole theory is much easier to understand if we only consider functions in L2. And exactly this is what we will do in this video again. We will discuss the geometric picture. So the functions are still 2 pi periodic, but now there should be square integrable. So just one more assumption for f. And then indeed we have a very nice geometric picture because fn of f is just an orthogonal projection. This is a big advantage because we can use all the knowledge we have about orthogonal projections already. In fact, what we will discuss today holds in general for inner products. It turns out the whole thing is a geometry argument which just uses that we have a right angle here. Here we just have the orthogonal projection and the normal component. And by definition, both are orthogonal to each other with respect to the inner product in L2. So we can just write it down, fn of f is orthogonal to the normal component. And the normal component is simply f minus the orthogonal projection. So there is no need to introduce a new name, obviously the difference is exactly what we need here. Okay, now this is something important to keep in mind, but back to the Fourier series now. An important question for the L1 case as for the L2 case is obviously what happens in the limit n to infinity. Please don't forget, the whole idea of this Fourier series is to approximate the function f in the end. But we still don't know if we get better if we increase n and if we reach f in the limit. But of course, this is exactly the important question we want to answer in this theory here. So what exactly happens if we send n to infinity? In the picture above, we would change the orthogonal projection in each step and maybe we reach f in the limit. This would mean that fn of f converges to f. In fact, this would be a very nice result, but it is not clear at all. Hence, there are a lot of questions related to that. For example, which conditions do we need for f to have this, and what limit is involved here anyway? Indeed, what we will do now is to talk about an L2 limit here. And as I already mentioned, the result we have now is very general. We have it in all inner product spaces. In other words, L2 here with an inner product is just a special case. However, it's exactly the case we need here, so let's immediately formulate it with L2. And please don't forget, the inner product we take here is the integral where the first component has the complex conjugation and we normalize it with 1 over 2 pi. Moreover, you also know we have nice orthonormal systems given in the trigonometric polynomials. And therefore, it's also easy to put them together into one infinite ONS. In fact, we can just write E where the index goes through all integers. So we have E minus 1, E0, E1, E2, and so on. In fact, the definition for an ONS also makes sense for such an infinite system. For example, you could just say every finite subset should be an ONS as well. And now as a reminder, ek is obviously just given by the exponential map. It simply sends x to e to the power ikx. However, as already mentioned, any other ONS would do the same job here. Okay, so this is the assumption for the proposition, and now we can say what it implies. Indeed, it tells us something for a chosen function f and the corresponding Fourier series. And please don't forget, the Fourier series has our Fourier coefficients ck. And they are just given as the inner product ek with f. And now what we get are some nice formulas for these ck's. Let's start with the first one, and I call it a. And there I want to ask, what is the difference between f and fnf? And we measure that with the norm we have in our inner product space. So important to remember, this is the L2 norm. And there you should know, this is just given as the square root of the inner product. So you see, this is also something we can do in any inner product space. So in our case here, it means we have the absolute value of this function squared inside the integral, and then we take the square root of everything. And since square roots are annoying for calculations, we usually just square the whole thing here. Okay, so now to answer the question from the beginning, if we want to have convergence in some sense, we want that this distance here gets smaller and smaller if n increases. Therefore, it's good to have a general formula for this distance. And in fact, this is a formula you definitely should remember. It just tells you, take the original length of f squared and subtract the sum of the coefficients ck squared. And since we have complex numbers involved here, we need the absolute value squared. So there we have it, this is the whole formula and it holds in general. And why this is the case, you immediately see when you recall the picture from before. Obviously, what we calculate here on the left hand side is just the length of the normal component. And since the normal component and the orthogonal projection are orthogonal to each other, we can just use the general Pythagorean theorem. This one is easy to prove in the inner product space, and it just states that the length of f squared is equal to the two lengths squared added here. So we have the length of the orthogonal projection squared here, plus the length of the normal component there. And then you see we just need one subtraction on both sides to get the formula here. And of course you have to calculate the inner product f and f with itself, but then you see it just results in that. Indeed, this is really simple because it just comes from the property of the ONS. So there we have it, this is already the proof of this general formula. Okay, now we have that, and now we know if we want to have a nice limit process in the end, we want that the right hand side here gets smaller and smaller if n increases. In other words, the sum over the ck squared here should get closer and closer to the norm of f squared. However, before we can say that, we can definitely state first that this sum is less or equal than the norm of f squared. Of course, this immediately follows from a, because the norm here, the left hand side, is definitely greater or equal than 0. Or if you want to explain it with the picture, the length of the orthogonal projection here is always less or equal than the length of f. So this is exactly what is stated here, and it holds for all n. And at this point I can tell you, this simple statement about the length of the orthogonal projection has a nice name. It's called Bessel's inequality. And since it holds for all n, it also holds in the limit process. There you can just use your knowledge about real sequences, because on the left hand side, we have a monotonically increasing sequence which is bounded from above. So it's a convergence sequence where the limit is also bounded by the same number. Moreover, you can also apply your knowledge about real series, because here we have a convergent series, which means that the sequence inside the series is a zero sequence. More precisely, this sequence of complex numbers has to converge to zero. In other words, Bessel's inequality implies that the Fourier coefficients converge to zero. So this is something to remember. Eventually, the contribution to the Fourier series gets smaller and smaller if n increases. However, Bessel's inequality is very nice, but not good enough for us, because as you remember, we want to have the right-hand side going to zero in the end. Hence, what we actually want in the end in the limit here is an equality. Therefore, the statement we get here is that we have the L2 convergence of the Fourier series to f, which means that this norm here goes to zero when n goes to infinity, if and only if we have the equality in Bessel's inequality. Which means that this convergent series is actually equal to the norm of f squared. And also there you should see this equivalence immediately follows from the formula we have in A. Hence essentially everything we have written down here follows from the Pythagorean theorem in any inner product space. So definitely something to remember in general, but now we can use it for our Fourier series. Moreover, now I can tell you the last equality we have here is called Parseval's identity. It just tells us if you add up all the Fourier coefficients squared, you get out the length of f squared. You could also see that as a generalization of the Pythagorean theorem with infinitely many sides. Therefore, this is a very nice result for Fourier series, but please note, at the moment we don't know if it actually holds. Indeed, we want to show that we have Parseval's identity such that we can conclude that we have the convergence. Therefore, this is exactly what we want to do in the next videos. So I really hope we meet again and have a nice day. Bye bye.
Cosine